Hey everyone, and welcome to our deep dive today. We're going to be virtually traveling to Singapore.
Oh, cool.
Yeah, to look at how physics is being taught
Okay.
in their junior colleges,
Right.
which are kind of like the last 2 years of high school here.
Gotcha.
We found some blog posts and web pages describing this really cool workshop where teachers got to use Java simulations to teach physics.
That sounds neat.
Yeah, it's really fascinating. What's really interesting is they're using open source simulations,
Oh.
meaning they're free to use and often customizable.
So that's a big deal for teachers.
Huge, because teachers in Singapore can then tweak these simulations to match their curriculum exactly, even aligning perfectly with the Singapore syllabus, which is kind of like their national set of standards.
Okay, like our standards, but for Singapore.
Exactly. So it's not like they're just handing a teacher
Yeah.
a prepackaged simulation saying, good luck with this.
Right.
They actually have the power to make it their own.
Exactly.
That's awesome.
And plus, the open source physics community is constantly creating and improving these simulations.
Oh.
They use a toolkit called Easy Java Simulation, or EJS, and there are literally hundreds of them out there.
Oh my gosh.
This particular workshop was all about getting junior college physics teachers comfortable using these tools.
That makes a lot of sense. So we've got these amazing simulations, but how does the workshop actually work? Do they just like throw the teachers into the deep end?
No, not at all. The workshop uses a very structured approach called the 5E instructional strategy, which is all about inquiry-based learning. And it's pretty popular in science education. It basically leads the students through these stages of engaging with a concept, exploring it, explaining their findings, elaborate on what they've learned, and finally evaluating their understanding. The teachers in this workshop actually got to design their own worksheets based on this 5E model.
So the teachers are learning too.
Yeah.
That's really cool. But with hundreds of simulations out there, how do they even know where to start?
Well, the workshop focuses on 9 specific Java simulations, which gives the teachers a solid foundation.
Okay.
The range is pretty impressive. Everything from simulating colliding carts to understanding how a bar magnet behaves inside a solenoid.
But what?
Solenoid.
What is that?
It's basically a coil of wire.
Okay. Bar magnet oscillating inside a solenoid. Doesn't exactly scream fun and engaging.
Yeah, I know.
Yes. Even if it is important.
Yeah.
Were there any simulations that you think would really hook students?
Oh, yeah, definitely. There's one called Ripple Tank
Oh.
that uses incredibly realistic 2D and 3D visualizations to show how waves interfere with each other.
Okay.
It's like having a virtual wave tank right on your computer screen.
Okay, that one does sound pretty cool. I could see students getting into that, but are we just talking like pretty pictures here? Or is there like real substance?
No, there's real substance there. The Ripple Tank simulation even has built-in hints and scientific measurement tools.
Ah.
So students can actually run experiments, gather data, and analyze their findings all within the simulation itself.
Wait, so they're not just passively watching waves?
Yeah.
They can actually experiment and test things out.
Exactly.
That's really cool.
And the workshop emphasizes that these simulations aren't static either. The Kepler's system simulation, which lets students play around with planetary motion, was actually improved based on feedback from students.
Oh, wow.
So it's this constant cycle of improvement and collaboration, which I think is pretty amazing.
Yeah, that is really cool. It's not like these simulations are just handed down from on high. There's actual input from the people using them.
Right.
That's awesome. What about teachers who weren't lucky enough to attend this workshop? Are these simulations like locked away somewhere?
Not at all. In fact, one of the most exciting things is that these resources are freely available online.
Oh, wow.
The workshop materials mention multiple online libraries where you can download tons of these EJS simulations. They even have ready-to-go worksheets created by other teachers, which is incredibly helpful.
Okay, I'm starting to see why you're so excited about all this.
Yeah.
It's not just about the technology itself. It's this open access and the collaborative spirit
Exactly,
that makes this so powerful.
And the teachers in this workshop are a perfect example of that. They come from various junior colleges across Singapore, and they're actively sharing their own worksheet designs and best practices. There's even an online community called the U in Physics chapter, where these teachers can continue collaborating and supporting each other.
So they form their own little think tank
Pretty much.
to make physics more engaging.
Exactly.
That's really cool.
And to make things even easier for other teachers, the workshop leaders created YouTube videos explaining how to use the simulations.
Wow, so they've really gone above and beyond to make sure these resources are accessible.
Yeah, I think so.
You know, it's one thing to hear about these incredible tools, but it's another thing to actually see them in action.
Mm.
Do you think we could maybe take a peek at a few more of these simulations and really dive into their potential?
Absolutely. Why don't we start with collision carts? It's a classic physics concept, but this simulation really takes it to a whole new level.
All right, collision carts. Let's smash some physics. What makes this simulation so special?
Well, you might remember those little carts on tracks from your own physics classes.
Uh-huh.
This simulation takes that basic concept and lets you manipulate all sorts of variables.
Oh, wow.
You can change the mass of the carts, their initial velocities, even add in different types of collisions like elastic or inelastic. It's like a virtual playground for exploring the laws of motion.
So instead of just watching a demo in class, students can actually design their own experiments and see what happens.
That's really neat.
And it goes beyond just playing around.
Yeah.
The simulation includes tools to measure things, like momentum and kinetic energy. Students can gather data, analyze it, and see for themselves how these concepts relate to each other. It takes those abstract formulas and brings them to life. Okay, I'm starting to get a feel for how powerful these simulations can be. But let's shift gears a bit and talk more about the 5E instructional strategy.
Okay.
It sounds like a pretty robust framework.
Oh.
But could you give us an example of how a teacher might actually use it with one of these simulations?
Sure, let's take the ripple tank simulation we talked about earlier.
Yep.
To engage students, a teacher might start by showing them a real-world example of wave interference, like ripples in a pond. Then they could introduce the simulation and challenge students to figure out how to create similar patterns.
So it's not just jumping straight into the simulation. There's a real-world hook to grab their attention.
Exactly.
I like it.
Then comes the explore phase, where students can play around with the simulation, changing the frequency and amplitude of the waves, adding obstacles, and observing how the interference patterns change.
Okay, so they're getting their hands dirty, so to speak, and figuring things out for themselves.
Yeah.
What happens next?
Next comes the explain phase. Students would share their observations, try to explain what they've seen, and maybe even come up with some hypotheses. This is where the teacher can guide them toward a deeper understanding of wave properties and the principles of interference.
I see. So it's a collaborative process, not just a lecture from the teacher.
Right.
That's cool.
And then comes the elaborate phase, which is where things get really interesting.
Okay.
The teacher might challenge students to use the simulation to solve a real-world problem, like figuring out how to reduce noise interference in a concert hall.
Ooh, that's a great example. It takes the concept beyond the textbook
Yeah.
and shows them how it applies to real life.
Exactly.
What about the final evaluate phase?
That's where students reflect on what they've learned. They might take a quiz, write a report, or even create their own simulation to demonstrate their understanding. The key is to make sure they've not just memorized facts, but actually grasped the underlying concepts.
It sounds like the 5E model really encourages a deeper level of learning and engagement.
Yeah, I think so.
But let's face it, not every student is going to be thrilled about physics.
True.
No matter how cool the simulations are. Do you think these tools can actually change students' attitudes towards the subject?
I think they absolutely can. Traditional physics teaching can be very abstract and equation-heavy, which can be intimidating for some students. But when you give them the power to visualize and interact with these concepts, it makes learning more fun and accessible.
So it's not just about making physics easier. It's about making it more engaging and relevant to their lives.
Precisely. And that can make all the difference in sparking their curiosity and fostering a genuine love of learning.
That's a great point. But one thing that keeps coming to mind, wouldn't using simulations all the time make students too reliant on technology?
That's a really important question, and it's a valid concern. Simulations are a fantastic tool, but they shouldn't replace real-world experiences entirely.
Yeah, that makes sense.
Ideally, they should complement each other.
So it's about finding the right balance.
Yes, exactly. For example, students could use a simulation to explore the concept of projectile motion and then head to the lab to test their predictions with a real projectile launcher.
Right.
The simulation gives them a foundation of understanding, and the hands-on experiment reinforces those concepts and allows them to see how things work in the real world.
I see. So it's about using each approach strategically to create the most effective learning experience.
Exactly.
But even with the best simulations and teaching strategies, there are always going to be challenges in physics education.
Right.
What do you see as some of the biggest hurdles that teachers face?
One of the biggest challenges is time. Physics concepts can be complex, and it takes time to build a solid understanding. Teachers are often pressured to cover a lot of material in a short amount of time, which can make it difficult to delve into topics in depth.
That makes sense. It's hard to foster that deep level of engagement when you're constantly rushing to the next topic.
Yeah, exactly. Another challenge is resources. Not all schools have access to the latest technology or well-equipped labs. And even with access to simulations, teachers need time to learn how to use them effectively and integrate them into their lessons.
So it's not just about having the tools, it's about having the support and training to use them effectively.
Yeah, that's a big part of it.
What about the students themselves? Do you see any particular challenges in getting them excited about physics?
Sometimes students come in with preconceived notions about physics being difficult or boring. That can be a real barrier.
I can see that.
And let's be honest, some physics concepts are challenging, and it can be frustrating for students when they struggle to grasp them.
So it's about finding ways to make those challenging concepts more accessible and relatable.
Absolutely. And that's where simulations can be a game changer. They can help students visualize abstract concepts, break down complex problems into smaller steps, and see the connections between different ideas.
It's about empowering them to become active learners rather than passive recipients of information. But let's shift our focus back to the teachers for a moment. The source material mentioned this amazing online community called the U in Physics chapter.
Oh, yeah.
Could you tell us more about that?
It's a fantastic example of teacher collaboration in action. It's an online platform where teachers who participated in the workshop can connect with each other, share resources, and get support from their peers. They're constantly uploading new worksheets, discussing teaching strategies, and helping each other troubleshoot any problems they encounter.
That's like a virtual support group for physics teachers.
Pretty much. And it highlights the importance of community in education. When teachers have a network of peers to lean on, they're more likely to feel confident and empowered in their classrooms.
It's about sharing the load and learning from each other's experiences.
Exactly.
But let's not forget about the unsung heroes behind all of this, the developers who create these incredible simulations.
Yeah, they're the real MVPs.
Could you tell us a bit more about the open source physics community?
It's a global network of physicists, educators, and programmers who are passionate about making physics education more engaging and accessible. They contribute their time and expertise to develop and share these simulations freely with the world. It's a truly collaborative effort driven by a belief that everyone should have the opportunity to explore the wonders of physics.
That's inspiring. It's like a grassroots movement to democratize science education.
I like that.
But what motivates these developers to contribute their skills and time to this project?
I think it's a combination of factors. There's a genuine desire to make a difference in education, to reach students who might otherwise struggle with traditional teaching methods. There's also the intellectual challenge of creating these simulations, of finding creative ways to represent complex concepts visually and interactively. And of course, there's the satisfaction of knowing that their work is being used by teachers and students all over the world.
It's about passion innovation and a shared commitment to making physics more accessible to everyone.
I think that's a great way to put it.
But let's be realistic. Developing these simulations must require a significant amount of technical expertise.
Oh, yeah, for sure.
What skills are needed to create something like the ripple tank simulation?
You're right. It's not a simple undertaking. Developers need a strong foundation in physics, of course, to understand the concepts they're trying to represent.
Makes sense.
They also need programming skills, particularly in Java, which is the language used for these EJS simulations. And then there are the visual design skills needed. To create those realistic and engaging graphics, it's a multidisciplinary effort that requires a diverse set of talents.
It's like a fusion of science, technology, and art.
I like that.
But let's get back to the big picture here.
Okay.
We've talked a lot about the benefits
Yeah.
of using simulations in physics education. But are there any potential downsides or limitations that we should be aware of?
That's an important question. Like any tool, simulations have their limitations. One potential downside is that they can oversimplify complex concepts. It's important to remember that simulations are models, and they can't capture every nuance of the real world.
So it's about using them judiciously, making sure students understand that they're not a perfect representation of reality.
Exactly.
Yeah.
Another potential issue is that simulations can be too passive. If students are just clicking buttons and watching things happen on the screen, they might not be actively engaging with the material.
So it's crucial to design activities that challenge students to think, critically experiment, and draw their own conclusions.
Absolutely. And finally, it's important to remember that technology is constantly evolving. The simulations that are cutting edge today might be outdated in a few years.
That's true. So it's about staying up to date
Mm-hmm.
and being willing to adapt as new tools and technologies emerge.
Exactly. The key is to view simulations as one tool in a larger toolkit and to use them strategically and thoughtfully to enhance student learning.
Well said. You know, as we've been diving into this topic, I've been thinking about all the other subjects that could benefit from this kind of approach.
Yeah.
Could we see open source simulations being used to teach history, literature, or even art?
That's a fascinating question, and I think the potential is enormous. Imagine students being able to step back in time and experience historical events through virtual reality simulations, or explore the intricacies of a literary text through interactive visualizations. The possibilities are endless.
It's about finding ways to bring those subjects to life and make them more engaging for students.
Exactly.
Before we get too carried away, with those possibilities, let's bring our focus back to the physics simulations
Okay.
we've been discussing. I'm curious to hear your thoughts on what the future holds for these tools.
I think the future is incredibly bright for open source physics simulations. As technology continues to advance, we'll see even more realistic and sophisticated simulations being developed. And as awareness of these resources grows, more and more teachers around the world will incorporate them into their classrooms.
It's about breaking down barriers and making quality science education accessible to everyone.
Exactly. And I think we'll also see a growing emphasis on collaboration and sharing within the open source physics community.
That's about working together to create a richer and more diverse library of simulations that meet the needs of learners worldwide.
I agree.
But let's step back for a moment and consider the broader implications of all this. What does the growing popularity of open source educational resources tell us about the future of learning?
I think it points to a shift towards more personalized and learner-centered education. Open source resources empower teachers and students to customize their learning experiences, to choose the tools and approaches that work best for them.
It's about giving learners more control over their own education.
Exactly. And it's about creating a more equitable and accessible learning environment where resources are freely available to everyone regardless of their background or location.
That's a powerful vision for the future of learning. But as we wrap up this deep dive, I want to leave our listeners with one final question to ponder. We've seen how open source simulations can transform physics education. But what other fields or disciplines could benefit from this approach?
That's a great question to consider. What areas of knowledge could be made more engaging and accessible through interactive simulations? Where could we leverage the power of technology and collaboration to create more powerful learning experiences?
Yeah, it really is amazing to imagine what could be done with these in other fields.
It is.
We've been focusing on physics, but who knows what creative simulations people could come up with for like history, literature, even music.
It's really about tapping into that human curiosity and making learning an adventure. And these simulations, especially the open source ones, really give educators that power to tailor the experience to their students' needs and interests.
That's a key point, isn't it? It's not about replacing teachers with technology.
Right. It's about giving teachers more flexibility, more tools to be even more effective.
And it's about empowering students to take ownership of their own learning when they can interact with these simulations, experiment,
Right.
and draw their own conclusions. It's a much more active and engaging process.
For sure.
You know, one thing that's really impressed me throughout this whole deep dive is this sense of community and collaboration.
Yeah.
It's not just about individual teachers using these simulations in their own classrooms. It's about them coming together to share ideas, resources, and support each other.
That's what makes the open source physics community so special. It's this global network of educators, physicists, and programmers, all dedicated to making physics education more engaging and accessible for everyone. They're constantly improving existing simulations, creating new ones, and sharing their knowledge freely with the world.
And it's not just about the technology itself. It's about that spirit of collaboration and innovation that drives this movement.
And for sure.
It's really inspiring to see people from all over the world
Yeah.
coming together to make a difference in education.
It is.
And it's also a good reminder that learning doesn't have to be confined to just the traditional classroom setting.
Right.
These open source resources are available to anyone with an internet connection, meaning students from all walks of life, anywhere in the world can benefit from them.
Exactly.
It's about breaking down those barriers and creating a more equitable and accessible learning environment for everyone.
I agree.
Well, I think we've covered a lot of ground today, from the nitty-gritty details of specific simulations to the broader implications for the future of education, what are some key takeaways you hope our listeners will walk away with?
First and foremost, I hope they'll be inspired to explore this world of open source physics simulations. There are so many amazing resources out there just waiting to be discovered.
And I hope they're encouraged by the collaborative spirit
Yeah.
and the passion for innovation that we've seen in this community.
Absolutely. And ultimately, I hope they see the potential for these simulations to transform not just physics education, but the way we approach learning in general.
It's about embracing new tools,
Yeah.
fostering collaboration, and never losing sight of the joy of discovery. So to our listeners out there, we encourage you to check out the links we'll be providing in the show notes. Dive into the world of open source physics simulations and see what sparks your curiosity.
You might be surprised at what you discover. And who knows, maybe you'll even be inspired to create your own simulations and share them with the world.
That's a great thought to end on. Thanks for joining us on this deep dive into the exciting world of physics education. Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible.